Okay, so this is Chapter 8, Electron Configurations and Periodicity. So from previous experiments, scientists knew that certain groups of elements had similar properties. That's how we came about the periodic table. Okay, so the example is that when you put group 1 metals into water, you get an explosion. Okay. In the last chapter, we talked about the quantum numbers, N, L, M sub L, and M sub S. So now we're going to look at where those electrons are and how that affects the chemical bonding. Okay, so we're going to start looking at the spins of the electrons. Okay, so Stern-Gerlach did an experiment where they shot hydrogen atoms between two magnetic plates, and every atom was deflected. Now, it was hydrogen because hydrogen only has one electron. So from that experiment, first they conclude that each atom must act as a magnet, and from the other thing is that there can only be the electron can have only two directions of spin, and they call that positive 1/2 and a negative 1/2. So this is a depiction from the textbook showing the fact that they're shooting electrons. This plate means that they're only getting the one coming through going straight, but as soon as it hit the magnetic field, some of them deflected up and others deflected down. There's a video. Here's the web address for that video that kind of shows the same thing. There's background on I don't have it playing here. I'll describe what's happening here as we go. Okay, so I have magnets. This is the South Pole, that's the North Pole. And they're going to start out the experiment by putting through magnetic particles, which is what this right here is. And they're basically going to shoot that through the magnetic pole, through the magnets. And when they do so, that one happened to orient itself so it lined up with the white with the blue. They turn it sideways, it goes through. So it didn't really matter how they oriented them, they got that. Okay, and what they have basically there is a magnetic pole. This is like the Earth magnetic system. Now they're going to do the same experiment with electrons instead, or hydrogen atoms. So here's a hydrogen atom shooting up, goes up, goes down, goes up, down, 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 up, down. And the key here is that all the electrons either went up, or all the atoms either went up, or they went down. There's none here that went into the middle field like the magnetic particles did. Okay? And so that's basically a recreation of or animation of the Stern-Gerlach experiments. Okay? So this is just showing the fact that you have the plus 1/2, which is symbolized by the up arrow, the negative 1/2, which is shown by the negative arrow. So, based on this, where are the electrons? Okay, I have electron configurations, which is just a distribution of the electrons around the available subshells. So it's a list of the subshells with superscripts denoting the number of electrons in each shell. And I have orbital diagrams, which is a diagram showing how the orbitals of the subshell are occupied. So carbon here has 6 electrons. It's element number 6, so a neutral carbon has 6 electrons. What I want to point out is that when I add up the superscripts here, I get 6 electrons. Okay, and the orbital diagram also shows me 6. There's 2 here, 2 there. That's 4 plus 1 is 6 total. The difference is that mainly in the P here. Okay, let me change colors. In the P here, okay, we know from previous that P has 3 subshells available. And so the difference between the electron configuration is we don't differentiate between the different P's, and in the orbital diagram, we do. The orbital diagram allows us to denote the quantum numbers of any given electron. So if I choose this electron here, okay, I can figure out what the 4 quantum numbers are. So N is equal to 2, and that came from this right here. L is equal to 1, and that came from the fact it's a P. Okay, the rest of this is kind of just theory. Okay, this is why our textbook doesn't go over it. I have 3 p orbitals, which again, let me switch colors because I have, it's getting crowded right here, a -1, a 0, and a 1. That was sticky color to choose. Doesn't show up well. I guess we'll go back to red. Okay. So a -1, a 0, and a 1. Okay. And these are arbitrary. Okay, meaning the fact that they're all equal energy. It could go in any order it wants to, but for the sake of doing the quantum numbers, I'm going to assign them these 3. So in that case, okay, then my M sub L is a -1 because it's in the first slot here. And because this is facing in the up direction, my M sub S is a +1/2. Okay, so those are the 4 quantum numbers. All right. Now, the Pauli exclusion principle, the definition in the book is that no 2 electrons can have the same 4 quantum numbers. So the difference between this, the 4 sets of quantum numbers here and here, they both have an N of 2, an L of 0, an M sub L of 0. This, however, will be a +1/2, and that would be a -1/2. So they don't have 4 identical quantum numbers. But basically, it also says that an orbital can only hold 2 electrons, and that no 2 electrons have the same spin can occupy the subshell. Alright, so this is a problem from the textbook. It says, which of the following orbital diagrams are allowed and which are not allowed according to the Pauli exclusion principle? Alright, so looking at this first one here, okay, I have 2 electrons both up and down. This one has 2 electrons up and down. This one, however, has 2 electrons, but they're both up. So that is not allowed. I can't have 2 electrons with the same direction. Okay? I really do like red better. Again, looking at this would be B in the textbook. Looking at B here, okay, these 2 also have the same spin. So that one is not allowed either. Looking at this one, 2, but they're opposite spins, 2 opposite spins, 2 opposite spins, 1 and 1. So this one is allowed. Okay. Looking at this one, 2 opposite. I have 3. So A, they're all the same spin, but also the fact that there's 3. There's not allowed to be 3, so this one is not allowed either. Okay. So this goes back to the last chapter, okay, the fact that S has 1 orbital, and each orbital can hold 2 electrons. P has 3, which is 6, D has 5, which is 10, and F is 7, which is 14. And this has to go back to the number of M sub L values that there are. So an M sub L for an S is 0. An M sub L for P is -1, 0, and 1. So there's 3 different values there. The M sub L values for D was -2, -1, 0, and 1 and 2. So that was 5 different values. Okay, so let me choose that one. Where am I at? So the M sub L here is a -2, a -1, a 0, a 1, and a 2. So there are 1, 2, 3, 4, 5 values here. And then 5 times the 2 gives me 10. And this is going to equal the number of lines that you draw when you do your orbital diagrams. And this is just the orbitals times 2. And that is the all of this presentation.